Alrighty, here we go. Geometric series. Now we are going on to geometric series as a function, and it's going to be really, really exciting. Oh, sorry, people, I'm not sharing my screen. Did it. Thank you for telling me. I am now sharing my screen. Okay, geometric series. We are going to make a new geometric series where the first term is the number 1. But this time the R, the ratio, is going to be the variable x. Dun, dun, dun. Now, that means that my series starts with 1, and then I add to that, what is 1 times x? X! My goodness. Yes. And then what's my next term? X squared, and so on. So this particular series is now the 4th series you are expected to come in knowing. So when you sit down for the AP test, you are expected to know the Maclaurin series for sine x, cosine x, and e to the x. You are additionally expected to be familiar with the geometric series as a power series. And this one you need to kind of put in a separate box from the other 3. The other 3, they have an interval of convergence of all real numbers. And as I showed you those polynomials over the screen with Desmos, you could see it going out farther and farther with those. This one only converges for a little bit. And it is based on the fact that it is a geometric series. If the R is x, and you combine that with what values of R give you converge, what values of R give you converge? And online, you guys following me? So what values can R be in order to converge? Oh, no, I said converge. Can you hear me correctly? Oh, it's just Jackie being Jackie, is that it? I felt like I needed to tease. I'm sorry, I shouldn't tease you. Stop. No teasing. Okay. What was I going to say? Oh, yes. I know that I get converge if I have a geometric series where the absolute value of the R is less than 1. That means that this series will converge anywhere that the absolute value of x is less than 1. And automatically, because this is made out of a geometric series, you don't have to test the endpoints. We already know diverge for the endpoints because that's what geometric series do. And I'm going to write it in sigma form. X to the n. However, this is starting at n equals 0. Previously, when we saw the geometric series of constants, the formula started at n equals 1. For the 4 different functions that you're expected to know a series for, they all have a sigma that starts at n equals 0. The other 3 that we learned earlier, we learned off of the Maclaurin-Taylor formula. But this one, I haven't even written to you what function this is yet. It comes from the fact that there is a formula for the sum of an infinite series. So if the absolute value of r is less than 1 in a geometric series, what is the formula for the sum? Wait, what? Should I ignore the conversation in chat? Because I see noodles squishy and I'm thinking I'm just going to ignore that. Okay. So do you guys remember the formula? It's okay. People forget it. Isn't it the first term over 1 minus r? Yes. And there it is typed in as well. Oh my goodness. And it's the sophomores answering online too. So there you go. I'm looking at the chat, and the sophomores are teasing each other, it looks like. Okay. Now, what is the first term of this specific geometric series? The first term is the number 1. What is the r of this geometric series? And it's specifically replaced with x. So this geometric series is representing a rational function. And that rational function is algebraic. I want to point out that it's algebraic because the other 3 that we did previously were not algebraic. They were trig and then an exponential. So again, you need to remember this particular series in a separate compartment from the other 3. And this is what you want to begin memorizing, is this whole business, that it converges when the absolute value of x is less than 1. You want to remember the function that this series is representing, and then know this series in first few terms, sigma, general formula, and all that. And now I'm going to walk you through a first example. We are going to take this known series and manipulate it to create other known series. However, huge warning. Okay, it was so nice when you had sine, cosine, and exponential function. You could see whether something was multiplying. You could see whether something was plugged in. You could see something divided. You are not going to see it with the algebraic. You have to figure it out. And it is not obvious. So I actually have to take this particular manipulation slower and talk about what it is. Don't do that to me. What it is you are looking for. Now I need to grab this. Nope, oh yes, I remember. I wanted to say something about this. There are many ways to go about algebra, manipulation, substitute, plug in, multiply, divide, a variety of ways that you can take this function and change it into the one you're given. Some ways will take a long time. Some ways will take a shorter time. So I'm giving you some advice. This right here is a beginning key to look at. You want this to be a 1 being added to an expression with the variable in the denominator. That's your key beginning point. And now I'm going to grab the first example. I'm going to move it up here because I know I've got work down further that I didn't erase yet from first period. Okay, so we're going to express this as a sum of a power series and find the interval of convergence. Now, also know that unless you are told otherwise, you don't want the center of the polynomial to change. So let's also look at what is the center of this polynomial. 0. And for the question of x doesn't equal 1, when you have a geometric series, you automatically know that when your r is positive or negative 1, you get diverge automatically. And our r is right now x. And let me get this out of the way. Now, right now, I have in that denominator that 1 that I told you you really want to have. That's your key first step. Now, look at what else is there in the denominator. And do you see what you need to do to make this denominator happen? And you want to think about substitution. Once you get this 1 being added to an expression that has x in it, you're trying to figure out what is being subtracted from that 1. I'm going to add some space. Okay, you're just, oh dear. It froze on me. I think it's going to restart itself. Okay, so while I wait for this to figure out if it wants to live or not, what do I need to plug into that x in the 1 over 1 minus x to make it become this? Okay, I need to tell it, go night-night. I know you're angry at me. I know. And then I'm going to get it back. Here we are. Apparently it didn't want me to add space. So if I take 1 over 1, yes, I know, 1 minus x, and I substitute for that x negative x squared, that will get me to what I needed. So before you get started manipulating any of the power series itself, you have to figure out what steps you're going to need to take to morph a 1 over 1 minus x into whatever is there. And the only thing you have to do is plug into x negative x squared. Into x negative x squared. So you start with the formula, and then you substitute in that negative x squared, and you want to simplify that. And I'm going to leave this up for a little bit. Notice that with the even exponents, this negative sign disappears. And very important, separate that -1 from the x squared, because you're going to be eventually doing more than just this first step. And you'll want to rewrite it in this format to prepare it for anything else that might need to be done. And notice it creates an alternating series. Now, for interval of convergence, I want you to realize that the only thing you changed was the r. It's still a geometric series. The r is -x squared. So that means this will converge as long as -x squared, absolute value, is less than 1. And then think about it a little bit. You might come to realize exactly what it is. Now, think about the fact that if I take numbers between -1 and +1 and I square them, they're still going to be between -1 and +1. I have the algebra also written up if you need to see that. And this is the algebra behind it. But I end up getting the same interval of convergence as I previously had. And one thing that's really fun to do with these problems is to go into Desmos, type in the function you believe your power series represents, type in the first few terms of this power series, and then see that it actually is pretty accurate for the interval of convergence. I've got to say, you have a resemblance to a former student, but that's probably close to everybody. I keep saying that to people, I think. Younger, but not older? Okay. It adds that you guys have a mask on, so all I see is part of your face. And I just keep seeing people who remind me of other people. But then again, you know, gene pool. It's wide and it's deep, but yet not at the same time. Okay, I need to erase some stuff here. You're not looking at this yet. We are now moving on to the next example. So just realize that that example was concluded with getting this interval of convergence. Okay, next example. You're going to come up with a power series. This one is actually quite a bit harder. And I realized I needed to add into the directions without changing the center, the fact that the center is 0 without changing that center. I'm going to rewrite this and I want to remind you of what I told you needs to be a primary beginning focus. You want this number to be a 1, but you need to make it a 1 without changing the fact that the center is 0. So I can't just subtract 1 to the denominator. If I do that, I'm going to change the center. And so just think about algebra. How can I make that become a 1? And you might see it in one of two ways. What is alternating series test in the near future, we're going to be looking at a certain aspect of it in the future. OMG. That's what you're missing. Okay. So either you see if I multiply top and bottom by 1/2, that'll happen, or you see that the denominator can have I can factor a 2 out of there. And whether you see it one way or the other way, you are winding up getting a 1/2 multiplying by 1/1 plus x over 2. And I want you to remember that you have not changed this function. But you have to analyze what's here and what's not here to figure out what to do to manipulate this function into this one. So at this point, you're actually ready. What can I do to 1/1 minus x to create this function? What do you see? You were right on the edge of it, though. Multiplying by 1/2 is one of the things that has to be done. And what I recommend you do, especially while you're just starting off doing these for the first time, write down in words what it is you're doing, and then do that to the 1/1 minus x just to see what that gives you. And yes, and then how do you make it? I'm going to insert some space carefully. I'm not going to go overboard. It didn't like it when I went overboard before. So if I'm multiplying by 1/2, this is what I now have. And then what can I do next to turn it in? And yeah, you're starting to see it now. Does everyone see that it's going to be a substitution? And I am going to substitute into my x a negative x over 2. And the next thing I'm going to do is actually do that. And I'm going to write it. Because I want to look at whether I'm creating what I intended to create. And when you're dealing with algebra, you have to check it a lot more carefully than when we were manipulating e to the x and sine and cosine. So just to make sure, is this what we intended? And can you see that we are now getting this by doing those two steps? Now, you always have to consider order of operations. Does it matter which one you do first? Will it change things if you reverse that order? It won't. But if you're not sure, just don't. So these are now telling me the steps of this is what I need to do to the geometric power series to create the new function. So I'm starting with my 1 over 1 minus x, which you can see here. And then I am multiplying by 1/2. So I'm taking every term of the series that I know, and I'm just multiplying a 1/2 all the way through. Then I want to substitute into the x's that I have in this previous problem right here, a negative x over 2. And it's important for possible future things that will happen next. You need to separate multiplication, division with the x in the formula. So that negative becomes a -1 to the n, and the divided by 2, I get 2 to the n with this divided by 2, but I also have this additional divided by 2, so the exponent becomes an n plus 1. Not too bad, right? But I warn you, the hardest part is understanding what steps you're going to need to do and just knowing what direction to even take. And so that is that problem resolved. Now, example 3, the textbook was kind because it gave you example 2 first and then example 3. If you had gotten example 3 right off the bat, it would have been overwhelming. So now what I want you to know is focus on the denominator first. When you see x cubed over x plus 2, you want to know that your first focus is the denominator. And within that denominator, the first thing that matters is getting this to be a 1. Now, I'm re-showing on this line what we did in example 2. We factored out a 1/2. We substituted in negative x over 2. And by doing those two things, I was able to get to the point of having this denominator. Now I'm going to take where I left off and multiply by that numerator, x cubed. So we left off with this formula. And if I multiply all of this by x cubed, how does that change the formula? In the formula itself, the only thing it changes is that the exponent is now n plus 3. Now, there is one thing that I did not say at the end of example 2 that you can see a little bit of the writing down here, interval of convergence. And actually, before I go back to that interval of convergence, let me ask you a question. If you know the interval of convergence of this series, can the x's that are allowed in its domain be affected if all the x's, or if every term is multiplied by x cubed? Does that change anything about what values of x create converge? So in other words, if you already know that for a particular x, this converges. And some of you are going to see it, some of you aren't, and that's fine. But you want to think about if the only thing you're changing on these terms is that you're multiplying by another x cubed. Let's see. R didn't change my multiplying by x. Right. Ooh, yes, that's actually a very good thing to notice. When we added the 3 on here, that did not change R. And brilliant thing to see. That is a really nice way to explain it, is to realize that with x to the n, you're dealing with a particular R. By adding 3, that doesn't change a geometric series R. Now, I do, however, need to go back and say that in example 2, when we were doing interval of convergence, what we plugged into R what we plugged into x is the R, and I did not change it from being a pure geometric series. So all I have to do is look at, okay, whatever I plugged into the x, that's the new R. Know this, if you aren't entirely sure whether you have a pure geometric series, if you're not entirely sure what I'm doing here with determining that the interval of convergence is -2 to 2, know this, you can always fall back on just do it the way we've been doing it. Start with the ratio test, check the endpoints individually, you'll still get the correct answer that way. You want to grow and begin to understand the change in the interval of convergence from one step to another step. That will help you to save time, but it's not an absolute necessity. So, the interval of convergence does not change in example 3 with that multiplication by x cubed. It does not change this from being a pure geometric series. It just changes the starting term. The starting term is now x cubed over 2, and the R is as it was before, I'm multiplying by another negative x over 2, multiplied by another negative x over 2. Whoever you see is to the power of n, or n plus a number, or n minus a number. Those are the items that make up the R in a pure geometric series. But be careful, because if any of these have an n multiplied by a number, then you need to consider that. That will change it. If you know it's pure geometric, it diverges at endpoints. Boom. Don't need to check it. And we love not having to check that. But I want to say, if you aren't entirely sure, just do it the way we did it before. Check them individually. And keep this in mind. If you're not sure if it's geometric or not, just test with the 3 terms is enough to test. Do you multiply by the same exact thing to go from the first to the second as you do to go from the second to the third? If you're multiplying by the same exact thing, then you are still dealing with a geometric series. That's a nice quick check that you can do. It doesn't prove that it's a geometric series, but it's a way you can do this to check. So today, let me make sure I'm clear to you what I have assigned. And I actually, no, didn't want to go there. Nah. I'm going to put up, this is, yes, okay. Okay, it's just about there. All right, so homework just got posted. And one of the things is going to be from the textbook, 3 through 9 odd. So let me go over to the textbook and point out to you what that is. Too far. Okay. You're going to be doing these odd problems, 3 through 9 odd. And then tomorrow, I'm going to take you a next step. But I realize how much I am doing it slowly. And I know that I need to spend a couple days making sure you're clear about this geometric series. So you're going to be doing just like we did with the examples. Figure out what you need to do to manipulate the 1 over 1 minus x to the function that you see there. And then do that to the series, determine that interval of convergence. Additionally, I have assigned, I decided to attach this, and that way, if you're not able to get into the College Board site, you can still do the problems. And these are on My AP. You can find the answers through the My AP site. What I'm trying to do with these is have you just review all of these tests. It's a lot of, well, it's 9 problems. For some of you, this might take a really long time, so let me make sure to clarify for you. If you are going to have put in a lot of time for homework and you're about to have to stay up late just to finish all of these problems, you can have an extension to continue working on them. I don't want you losing sleep. For some people, they're going to breeze through this and you can be disgusted by them and everything. But I know that we need to practice these tests before I quiz you on them. So I want to make sure to give you sufficient problems to be practicing. And I should probably set up a link additionally. Do all of you have links for AP Classroom right on your computer? Yeah, go to that link and then you'll see that this is assigned. Of course, this is, oh, I'm on the school's Wi-Fi. That's why everything's taking so long. Okay, yep, this is called school Wi-Fi. Anyway, now, the rest of the class can be spent with any homework questions that you have. There we go. I got finally to just the site, and I've already given up on it. So, textbook problems. I can go over questions. Let me tell you that I went over 2 problems with period 1, and I might actually save some time by just throwing these your way, especially since I already have it up. And it is from section 11.8, number 25 and 23. I got through those 2 during period 1 this morning. And if you have other homework questions you want to see, type it into chat. So for number 25, the directions were finding the interval of convergence. So remember that you always start off with ratio test, plug in n+1, multiply by reciprocal, make sure you say limit as n approaches infinity in front of that absolute value. Then realize what does cancel and what doesn't cancel. When finding if something is absolutely convergent, do we have to say the tests we used? If it's free response, state the test you used. Because some of them had, say all the tests. Realize that you should be using up to 2 tests. If you think you're using a third one, oh, wait, I just remembered. Because you might, oh, yeah, you're right. You can use up to 3. I forgot. You might have to do a comparison test. So, yes, just state all the tests you're using. Yeah. Just take the time to write it out. So with this particular inequality, you get the result of the ratio test, and you know you get converge if the absolute value is less than 1. You know you get diverge for greater than 1, but you aren't sure at equal to 1. And it's just the answer key would say absolutely converges. Okay. Oh, you mean without stating the test used?
Yeah, they would just say the interval absolutely converges, and just like literally like that.
Okay.
Like, I used 3 tests, why wouldn't you say that? So
okay. Because probably what they have is, if you look through the actual solutions, they show the process, and then all they do at the very end is answer the one question that was asked. But in a free response, you're showing your work as you go through it and stating the tests you use as you go through it. Now, realize what you can do to save yourself time. If you factor this 4 out and then divide by that 4, you can then figure out, let me erase this and clarify what is what. And where did I go? There I am. Okay. If you take what is in the absolute values and force this to become just a 1 times x in front, so I had to factor a 4 out and then divide by 4. It's positive, so it doesn't change the inequality. The center is found by whatever makes that parentheses equal 0. So what is the center of this? You just saw me erase it, so. Does everyone see that the center is negative 1/4? That's what makes that parentheses equal 0. If x is multiplied by 1, the other side is your radius. So if you know the center and you know the radius, I find that a faster way to solve this inequality. You don't have to show or even do the solution through algebra. Once you have that inequality, you're allowed to just state, this is the interval of convergence so far. I have found, though, if you can determine the center and the radius, then you can just literally write down, okay, the center is negative 1/4. From there, add the radius and subtract the radius to get the edges of that interval. This is the fastest way to go through solving these inequalities. From there, you have to check the endpoints. With checking the endpoints of negative 1/2 and 0, you're going to go back to the original equation, substitute into Vx, negative 1/2. When this is negative 1/2, multiply by 4, I get negative 2, add the 1, I get negative 1. When I plug in 0, I end up with just 1 to the n on top, so that simplifies to just 1. And then when x is negative 1/2, I know it converges by alternating series test. When x is equal to 0, it converges by p-series. So the interval of convergence includes the endpoints. Then for number 23, start off with ratio test. Plug in an n plus 1 everywhere you see an n, and then see what cancels. And then understand that once you look at what's left over after the cancellation, x only gets to represent a real number. That's it. It doesn't actually represent infinity, even though we might say that we're looking from negative infinity to positive infinity for the x. We aren't taking infinity. So this, if it is a real number at all times, it is multiplying by infinity. And it will be infinity as long as it's not infinity times 0. Infinity times 0 is indeterminate form. And so you can't actually solve this limit for what makes that x equal to 0. But the thing that makes that x equal to 0 is the center. And we looked last week at the fact that it always converges at the center. So realize the answer is infinity as long as x is any real number other than 1/2. And then you're expected to know that it converges at the center. The radius of convergence is 0. And the interval of convergence is just that. We still have, wait a minute, now 2 minutes. Okay, we're down to 2 minutes. Are there other homework problems you needed help with? It's actually harder to explain in the classroom, isn't it? I'm going to stop recording. We now have only 1 minute left. So, yeah.